Hi everyone, I hope you all are good. So, our topic is electrostatic potential and capacitance, NCERT Exemplar problems 2.1 to 2.30. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. So our first problem, example problem 2.1, multiple choice questions, and the problem is a capacitor of 4 microfarad is connected as shown in the circuit. The internal resistance of the battery is 0.5 ohm. The amount of charge on the capacitor plates will be. So we have to find the amount of charge on the capacitor plates. This is a capacitor 4 microfarad and there is a resistor 10 ohm which is connected in series with it. There is a battery of 2.5 volt which is having internal resistance 0.5 ohm, and another 2 ohm resistor is connected parallel to the battery. So all these three things, this combination of capacitor and this 10 ohm resistor, this battery and this 2 ohm resistor is connected in parallel. So options are 0, 4 microcoulomb, 16 microcoulomb and 8 microcoulomb. So I will give you some time to think about it. So this is the question again. Answer is option D, 8 microcoulomb. So let's see the solution. So what is the thinking process for this question required? In this problem, three parallel branches of the circuit. These three parallel branches, one branch, second branch and third branch of circuit can be considered in parallel combination with one another. Therefore, potential difference across each branch is same. So potential difference across each branch is same because they are in parallel. The capacitor offers infinite resistance in DC circuit. So capacitor will store charges, and when the charges stored on this capacitor become maximum, the flow of current through this capacitor will become zero. So it will offer infinite resistance, which means zero current in DC circuit. So in DC circuit, capacitor will offer infinite resistance due to store of maximum charge on its plate, and therefore no current flows through capacitor and 10 ohm resistor. So it offers infinite resistance to the circuit in DC circuit. So no current flows from this branch. So there is no current through 10 ohm resistance also, leaving zero potential difference across 10 ohm resistance. So since there is no current flow of current from this through this 10 ohm resistor, therefore potential drop across this 10 ohm resistor is zero. Thus potential difference across lower and middle branch of circuit is equal to the potential difference across the capacitor of upper branch. So potential difference across this branch, middle branch and this lower branch, potential difference across these two branches is equal to the potential difference across this capacitor, because potential drop across this 10 ohm resistor is zero because there is no flow of current through this branch, upper branch, due to presence of capacitor. So only potential difference will be there, which is potential difference across the plates of capacitor. So potential difference across lower and middle branch of the circuit is equal to the potential difference across capacitor of upper branch of the circuit. So answer D, current flows through 2 ohm resistance from left to right is given by I equal to V upon R plus R. So what is the current through 2 ohm resistor? This resistor is not considered here because there is no flow of current through this resistor. Only this resistor is being considered. So the current through 2 ohm resistance is 2 ohm. What is the net resistance in this circuit? One is this C. There is no flow of current from this upper branch, so this branch is not considered when we want to find the current in the circuit. So this branch will not considered. Now this branch is being cancelled for now. Now this battery is in series with this 2 ohm resistor. This battery is in series with this 2 ohm resistor. So internal resistance of battery itself is 0.5 ohm. So the total resistance in the circuit is this internal resistance of the battery plus this 2 ohm due to series combination of resistors. So total resistance in the circuit now is R, capital R, which is external resistance 2 ohm, and small r, which is internal resistance of the battery. And what is the potential? This V is equal to the potential difference created by this battery, voltage of the battery, 2.5 volt upon 2 plus 0.5, which is equal to, after solving, 1 ampere. So current through the circuit is 1 ampere. So current will flow from here to here, not in this section, because capacitor offers infinite resistance. Okay, now a capacitor of 4 microfarad. So capacitor is of 4 microfarad. Again same diagram. The potential difference across 2 ohm resistance is V equal to IR. Now we have to find the potential difference or potential drop across this 2 ohm resistor, which is equal to current flowing through this 2 ohm resistor into the resistance of this 2 ohm resistor. So potential difference across this 2 ohm resistor is V equal to IR. 1 ampere into R equal to 2 ohm. So potential difference across this 2 ohm resistor is 2 volt. Okay, so if potential difference across this 2 ohm resistance is 2 volt, it means all the branches are parallel. So potential difference across all the branches will be 2 ohm. But this battery is of voltage 2.5 volt. Why the potential difference across this battery is 2 volt also? Because there is internal resistance of the battery, due to which there is some potential drop across the battery also, and it reduces the 0.5 volt across the battery, and net potential across the battery is 2 volt also. Since capacitor is in parallel with 2 ohm resistance, so it has also 2 volt potential difference across it. Since this capacitor is in parallel with this 2 ohm resistor, so it has also 2 volt potential difference across it. The charge on the capacitor, now we can calculate the charge on the capacitor. We know the capacitance, we know the voltage across the capacitor, so we can find the charge by the formula Q equal to CV. So Q equal to CV, C is 4 microfarad into 2 volt. So charge on the capacitor is 8 microcoulomb. Got it? Note the potential difference across 2 ohm resistor solely occurs across capacitor, as no potential drop occur across 8 ohm resistance. So this potential difference 2 volt only occurs across the capacitor, since this potential difference across this 10 ohm resistor is 0. Why 0? We have already discussed about it. So second question, a positively charged particle is released from rest in an uniform electric field. The electric potential energy of the charge is, option 1 remains a constant because the electric field is uniform, increases because the charge moves along the electric field, decreases because the charge moves along the electric field, decreases because the charge moves opposite to the electric field. So these are the 4 options. Since electric field is uniform and a positive charge, we know that positive charge will feel the force in the direction of electric field. And since electric field is conservative, work done by electric field is conservative. Okay, so the potential energy decreases because work done by conservative forces is stored in the form of potential energy, negative potential energy, because potential energy increases when the work done is by conservative forces. Okay, so firstly this positively charged particle will move along the electric field, and since it is moving along the electric field, what happens? Its potential energy decreases. So what is the correct option? We will see. So I will give you some time to think about it. So again, same question, and the answer is C. Decreases because the charge moves along the electric field. Okay, so electric potential energy will decrease. Okay, solution. So let me see the reason behind it. So what is the thinking process for this question? In this problem, the relationship between E and V is actualized. Okay, you know the relation between electric field and potential difference. So electric field is equal to minus dV by dr. So electric field is in the direction of decreasing potential, hence decreasing potential energy. So electric field is in the direction of decreasing potential energy or decreasing potential. So if there is a positive charge, it will move along the electric field due to the force on it. So the potential energy of this positive charge will decrease in the direction of electric field. Okay. So let's see the answer. The direction of electric field is always perpendicular to one equipotential surface maintained at high electrostatic potential to the other equipotential surface maintained at low electrostatic potential. Okay, so direction, what is the direction of electric field? Is always perpendicular to the equipotential surface maintained at high electrostatic potential to the equipotential surface maintained at low equipotential electrostatic potential. Okay, so what they are saying, that electric field is from high electrostatic potential to low electrostatic potential, and the second thing they are mentioning, that electric field is perpendicular to the equipotential surface. Okay, so after combining, we can say electric field is from higher potential to lower potential and perpendicular to the equipotential surface. The positively charged particle experience electrostatic force along the direction of electric field from high electrostatic potential to low electrostatic potential. So it will experience the force in the direction of electric field. So we know that potential in the direction of electric field decreases according to the relation of electric field and potential. So potential energy also decreases. That is, that positive charge will go from high electrostatic potential to low electrostatic potential. Thus the work is done by the electric field on the positive charge. Hence electrostatic potential energy of the positive charge decreases. So work is done by the conservative forces. So potential energy will decrease. Okay, why A option is incorrect? A option was remains a constant because the electric field is uniform. This is incorrect because even though the electric field is uniform, the positively charged particle will still experience a force. Okay, even electric field is uniform or it can be non-uniform, like positively charged particle will experience force. It is not dependent on the uniformity or non-uniformity of the electric field. It will experience force and move in the direction of electric field, causing a change in the electric potential energy. Why B option is incorrect? What was B option? Increases because the charge moves along the electric field. This is incorrect because as the positively charged particle moves along the direction of electric field, it moves from a region of higher potential to a region of lower potential, because direction of electric field is from higher to lower. So it is moving in the direction of electric field. So it is going from region of higher potential to region of lower potential, resulting in decrease in electric potential energy. Why D option is incorrect? What was D option? Decreases because the charge moves opposite to the electric field. This is incorrect because positive charge will experience force in the direction of electric field only. Okay, so this option is incorrect because they are saying that because the charge moves opposite to the electric field. So this is incorrect because the positively charged particle will naturally move in the direction of electric field, not opposite to it. If it were to move opposite to the electric field, it would require external work to be done on it, which is not the case here. Okay. So the next question, example problem 2.3. Figure shows some equipotential lines distributed in a space. A charged object is moved from point A to point B. So this is the equipotential surfaces shown, and these are the A and B points shown on all diagram. So from going A to B, so we have to look upon the options. The A option is given. The work done in figure 1 is the greatest. The work done in figure 2 is the least. The work done is same in figure 1, 2 and 3. And the work done in figure 3 is greater than figure 2 but equal to that in figure 1. So these are the 4 options. So now you can see also potential value of potential is given for each equipotential surface. So in first diagram, point A is on 20 volt equipotential surface and B on 40 volt equipotential surface. In second figure, A is on 20 volt equipotential surface, B on 40 volt equipotential surface. In figure 3 also, A is on 20 volt equipotential surface and B on 40 volt equipotential surface. Since this diagram is somewhat different from other two, but potential difference between these 2 points is same in all the 3 figures. Okay, and we have to move a charge from A to B. So let's see what is the work done and which option is correct. So I will give you some time to think. So this figure again, 3 figures, solution, and the answer is C. The work done by electrostatic force W12 equal to QV2 minus V1. Here initial and final potentials are same. So we are only concerned with the magnitude of charge to be moved from A to B. Okay, so it can be any charge and it is proportional to the potential difference between 2 points, which is same in all the 3 questions. A is at 20 volt and B is at 40 volt. So potential difference is same in all the 3 diagrams. Although this diagram is somewhat different from other two, but it doesn't mean that we only want to see the potential difference between 2 points. We are not concerned with the configuration of the diagram. Okay, so V2 minus V1 in all the 3 diagram is 20. 40 minus 20 is 20. So here initial and final potentials are same in all the 3 cases and same charge is moved in all the 3 cases. So work done is same in all the 3 cases. Got it? So next example 2.4. The electrostatic potential on the surface of a charged conducting sphere is 100 volt. 2 statements are made in this regard. So first statement is at any point inside the sphere, electric intensity is 0. So this is first statement. At any point inside the sphere, electrostatic potential is 100 volt. which of the following is correct statement? So any charge conducting sphere is there, and the electrostatic potential on the surface of this sphere is 100 volt. Two statements are made. First is, at any point inside the sphere electric intensity is 0, and second statement is, at any point inside the sphere electrostatic potential is 100 volt. Which of the following is correct? So these are the four options. S1 is true, but at S2 is false. Both S1 S2 false. S1 is true, S2 is also true, but S1 is the cause of S2. Or S1 is true, S2 is also true, but the statements are independent. So these are the four options. So I will give you some time to think about it. So correct option is C. S1 is true, S2 is also true, and S1 is the cause of S2. Okay, so let's see how. In this problem, the electric field intensity E and electric potential V are related as. So it can be solved using relation between electric field and potential, and they are related as E equal to minus dV by dr. Okay, so since potential at surface is 100 volt, okay, so we know that, but if there is a charge conducting sphere and there is a potential at surface 100 volt, we know that inside the conductor electric field intensity is 0, and since inside it is 0, so minus dV by dr is equal to 0 inside the conductor, which means V is constant inside the conductor, and it is equal to the potential at the surface. So electric field intensity E equal to 0 inside the conductor suggests that dV by dr equal to 0. So dV by dr equal to 0 means there is no variation of potential inside the conductor. So between inside the conductor, between any 2 points, potential difference is 0. Potential is same inside the conductor at any point. So this implies V is equal to constant inside the conductor. So both statements are true, and also S1 is the cause of S2. Does E equal to 0 inside the charge conducting sphere causes the same electrostatic potential 100 volt at any point inside the sphere? So this thing E equal to 0 causes this thing, same electrostatic potential 100 volt at any point inside the sphere. Note, V equals 0 does not necessarily imply E equal to 0. So if V is equal to 0 at any point, not necessarily implies E equal to 0 there. For example, the electric potential at any point on the perpendicular bisector. So in the case of dipole, we know that in the midpoint of the dipole and perpendicular to the dipole, there is a plane called equipotential surface, where potential due to the both charges of the dipole is 0 on this plane. So potential is 0 at this plane. The electric potential at any point on the perpendicular bisector due to the electric dipole is 0, but electric field at that point is not 0. It has some value on the equatorial line or equatorial plane, but potential on the perpendicular bisector, or we can say equatorial plane, is 0 due to dipole. So it is not necessary that E should be 0 if V is 0 somewhere. Okay, and E equal to 0 does not necessarily imply that V equal to 0. Okay, so if E is 0 somewhere, it does not necessarily imply that V equal to 0. Example, the electric field intensity at any point inside the charged spherical shell is 0, but there may exist non-zero electric potential, as we have mentioned earlier, or in this question also. Electric field is 0 inside, but potential is not 0 inside. Okay. Equipotentials at a great distance from a collection of charges whose total sum is not zero are approximately. So equipotential surfaces at a great distance from a collection of charges. There is a collection of number of charges whose total sum is not zero. So there is a collection of charges and the sum of all the charges on all the charges present in the collection is not zero. So their equipotential at a greater distance, when we are experiencing the equipotential surface at a greater distance from these collection of charges, they approximately look like option A, spheres, planes, paraboloidals or ellipsoids. So I will give you some time to think about it. So answer is A, spheres. Solution. The answer for this question is, okay, in this problem the collection of charges whose total sum is not zero with regard to a great distance can be considered as a point charge. So if there is a collection of charges and we are experiencing or analyzing these collection of charges from a great distance, so they will appear as a point charge if we are analyzing these collection of charges from a great distance. So these collection of charges will appear as or can be considered as a point charge. So equipotential surfaces due to a point charge are spherical in shape as electric potential due to point charge Q is given by. Okay, so a collection of charges can be considered as a point charge if we are analyzing or viewing this collection of charge from a great distance. So V equal to Ke Q by R. So this is the potential due to a point charge. This suggests that electric potentials due to point charge is same for all the equidistant points. Okay, so for fixed R, for equidistant points, fixed R from a point charge, electric potential due to point charge is same for all the equidistant points. The locus of these equidistant points which are at same potential form spherical surface that we already studied in the equipotential surfaces, that due to point charges what shape of equipotential surfaces are there? Spherical. Okay. So plane equipotential surfaces are typically associated with the uniform electric field, not point charge, such as those created between the two parallel plates with opposite charges. In the plates of capacitor, there is a uniform electric field. At a great distance from a collection of point charge, the field is not uniform. Okay, so at a great distance from a collection of point charge, field is not uniform, and thus equipotential surfaces cannot be planes. So planes cannot be the answer. And why paraboloidals is not the answer? Paraboloidal equipotential surfaces are characteristic of specific charge distribution such as line charge or dipole in certain configuration. However, at greater distance from a collection of charges whose total sum is not zero, the field resembles that of a point charge, not a configuration that would produce paraboloidal equipotentials. So this is the reason why paraboloidals are not taken. Paraboloidals are for specific charge configuration like line charge or dipole in certain configuration, not for a point charge, and we are considering collection of charges from a greater distance as point charge. And why there are answer is not ellipsoids. Ellipsoids equipotential are associated with more complex charge distribution, such as involving multiple charges in specific arrangement. So ellipsoids, this type of equipotentials are formed when there is a complex charge distribution, such as those involving multiple charges in specific arrangements. At a great distance, the influence of individual charges blends together and field approximate that of a single point charge, leading to spherical equipotential rather than ellipsoid ones. So ellipsoid is not the answer here. So next example 2.6. a parallel plate capacitor is made of two dielectric blocks in series. So these two dielectric blocks K1 and K2 are in series and they are of thickness D1 and D2. One of the block has thickness D1 and dielectric constant K1 and other has thickness D2 and dielectric constant K2 as shown in the figure. This arrangement can be thought as a dielectric slab of thickness D equal to D1 plus D2. So this arrangement can be thought as a dielectric slab. This whole configuration or whole arrangement can be considered as a one dielectric of thickness D1 plus D2. And effective dielectric constant K, we have to find the effective dielectric constant. If this arrangement is considered as a whole one dielectric slab and the thickness, total thickness of the dielectric is D1 plus D2, then we have to find the equivalent or effective dielectric constant K. Okay, so these are the options. A option K1 D1 plus K2 D2 upon D1 plus D2. B option K1 D1 plus K2 D2 upon K1 plus K2. C option K1 K2 D1 plus D2 upon K1 D1 plus K2 D2. And D option is 2 K1 K2 upon K1 plus K2. So I will give you some time to think about it. So here is the question again. Answer C. So C is the correct answer. K1 K2 D1 plus D2 upon K1 D1 plus K2 D2. So how this answer is coming? We'll see that. Solution. So what is the thinking process for this question? In this problem, the system can be considered as the series combination of two capacitors which are of thickness D1 and filled with dielectric medium of dielectric constant K1 and thickness D2 and filled with dielectric medium of dielectric constant K2. So we can consider this system as two capacitors. One capacitor and two capacitors connecting side by side. One capacitor is having K1, this K1 medium completely inserted between its plates, and another capacitor having K2 dielectric medium inserted between its plates. So we can consider it as two capacitors connected side by side in series. Okay, so two capacitor which of thickness D1 and filled with dielectric medium completely of dielectric constant K1 and other capacitor of thickness D2 and filled with dielectric medium of dielectric constant K2 completely. So let's find the capacitance of the two capacitors. So the capacitance of parallel plate capacitor filled with the dielectric block has thickness D1 and dielectric constant K2 is given by C1 equal to K1 epsilon naught A upon D1. Okay, so for this first dielectric, K1 dielectric and this D1 thickness. So to calculate the capacitance for this first capacitor, this capacitor having separation between its plates D1 and dielectric medium inserted between its plates K1. So capacitance C1 is K1 epsilon naught A upon D1. So this is the capacitance for this capacitor. Now capacitance for this D2, for this capacitor having D2 separation. Similarly, capacitance of parallel plate capacitor filled with dielectric block has thickness D2 and dielectric constant K2 is given by this. C2 is equal to K2 epsilon naught A upon D2. So this is the capacitance of this second capacitor. Since the two capacitors are in series combination, since these two capacitors are in series combination, this first capacitor, this is the first capacitor, this one, this is the first capacitor, and this is the second capacitor, this capacitor and this, the capacitor formed by the plates, this plate and this plate is first capacitor, and capacitor formed due to this plate and this plate is second capacitor. Okay, so these two capacitors are in series. Since the two capacitors are in series combination, the equivalent capacitance is given by, so in series capacitance can be calculated as 1 by C. This is capacitance of combination equal to 1 by C1 plus 1 by C2. So we have calculated C1 and C2, put these values in this, C equal to C1 C2 by C1 plus C2, and put these values of C1 and C2 in the formula, and after solving this you will get this equal to K1 K2 epsilon naught A upon K1 D2 plus K2 D1. So this thing we have achieved. Now but the equivalent capacitance is given by, now if we consider according to the last line of the question, this arrangement can be thought as a dielectric slab of thickness D1 plus D2 and effective dielectric constant K. So if we consider these two dielectric as one dielectric slab and this two capacitors as whole one capacitor, and this is a separation D1 plus D2 is the total separation between the plates of the capacitor. This D1 plus D2 is the separation between these two capacitors. Okay, the capacitor, and this two dielectric slabs is considered as one dielectric slab of equivalent capacitance K. Okay, so the capacitance will be C equal to K epsilon naught A. K is the equivalent capacitance upon D1 plus D2. Okay, so these two dielectrics are now considered as a one dielectric slab of thickness D1 plus D2, and the dielectric constant of this slab formed due to these two dielectrics is considered as K, equivalent dielectric constant. Okay, effective dielectric constant. So on comparing this C and the C we calculated earlier, on comparing these two C, we will get equivalent capacitance is equal to K1 K2 D1 plus D2 upon K1 D2 plus K2 D1. So on comparing both C's, we will get the value of effective dielectric constant K, which is equal to this. Okay, note, for the equivalent capacitance of the combination, thickness is equal to the separation between two plates D1 plus D2 and dielectric constant K. So for equivalent capacitance of the combination, thickness is equal to the separation between the plates D1 plus D2 and dielectric constant K. Okay, so our next question, exemplar problem 2.7, and now this question is multiple choice, more than one option can be correct. Okay, so consider a uniform electric field in Z direction. So there is a uniform electric field which is in Z direction. The potential is constant. Okay, so the potential is constant and the options are in all space. Okay, they are asking the potential is constant and the option are in all space for any x for a given z, or for any y for a given z, or on the xy plane for a given z. Okay, so we have been given only the electric field which is uniform and in z direction. We have to find what is the potential. So the question is asking that potential is constant on where? Potential is constant where? So there are four options given: in all space, for any x for a given z. If we fix the value of z, then for any x potential will be same or not. If we fix the value of z, then potential on any y will be constant or not. Or if we fix the z, potential on xy plane will be constant or not. So we have to find this. So I will give you some time to think about it. So again same question, and the answer is B, C and D. Okay, so how this answer is coming? So this is a diagram we have seen when we were deriving the relation between electric field and potential. So electric field is in the direction of decreasing potential. These are two equipotential surfaces. Okay, so this is the potential for lower equipotential surface is V. For upper equipotential surface is V minus delta V. So in this direction potential is decreasing, so electric field is in the direction of decreasing potential. So this diagram we have analyzed before. Here the figure, electric field is always remain in the direction in which potential decreases steepest. Its magnitude is given by the change in the magnitude of potential per unit displacement normal to the equipotential surface at that point. So electric field is always perpendicular or normal to the equipotential surface, and its magnitude is given by change in magnitude of potential, which is dV per unit displacement upon dl, normal to the equipotential surface. And negative sign shows what? That electric field is in the direction in which potential decreases steepest. So now the electric field is in z direction, suggests that equipotential surfaces are in xy plane. Okay, so equipotential surface will be perpendicular to the electric field. So if electric field is in the direction z, then equipotential surface will be in the direction of, so equipotential surface will be in xy plane. Okay, if electric field is in this direction z, so equipotential surface will be in which plane? XY plane, like this. Okay, therefore the potential is a constant for any x for a given z. So potential is constant for any x if we fix the z. If we fix z for any value, then there will be at that z there will be a equipotential surface perpendicular to the z axis. So for any x on this equipotential surface, potential will be constant. And same for y. If we fix the z value, then there will be equipotential surface there on which for any y potential will be constant on the xy plane for a given z. Note, the shape of equipotential surface depends on the nature and type of distribution of charge. Okay, for example, point charge leads to produce spherical surfaces, whereas charge distribution produces, line charge distribution produces cylindrical equipotential surface. So equipotential surface depends upon the distribution of charge. So option A is incorrect because the uniform electric field in the z direction implies that potential varies linearly with z, whereas therefore the potential cannot be constant in all space. So potential is only constant in xy plane, not in z direction, because electric field having direction in the z axis or in z direction. So potential will decrease in the direction of electric field. So potential will decrease as we move on z axis in the direction of electric field. So potential is not constant on z axis or in z direction. That's why option A is incorrect. Okay, so potential is not constant, cannot be constant in all space. So next question, example 2.8, equipotential surfaces. So what option is correct for equipotential surfaces? So 4 options are given. First one is, are closer in regions of large electric fields compared to the region of lower electric fields. So equipotential surfaces, are equipotential surfaces closer in the region of large electric fields as compared to the lower electric fields? Second option, will be more crowded near sharp edges of conductor. Third option is, C option is, will be more crowded near regions of large surface charge density, large charge density, or, and D option is, will always be equally spaced. So I will give you some time to think about it. So the answer is A, B, C. These three options are correct. Only D option is incorrect. Solution is, so what is the thinking process for this question? In this problem, we need a relation between the electric field intensity E and electric potential V. Okay, so at the time when I explained this topic, I mentioned that this is important topic. Many questions are based on this topic. So relation between electric field intensity E and electric potential V. Okay, so we know that E equal to minus dV by dr. Okay, this is the relation. So equipotential surfaces, if are closely spaced, okay, when there is a high electric field intensity at that region. Okay, so electric field intensity is inversely proportional to the spacing between the equipotential surfaces. So if electric field is high at some region, okay, so this spacing between the equipotential surfaces will be less. Okay, answer ABC is correct. The electric field intensity E is inversely proportional to the separation between the equipotential surfaces. So this E is inversely proportional to this separation between equipotential surfaces. So equipotential surfaces are closer in the region of large electric fields. So in the region where electric field is large or it is of great amount, then their surfaces are closer. This dr is small. Since the electric field intensity is large near the sharp edges, so at sharp edges we know that there is a large surface charge density at sharp edges. Sharp edges of charge conductor and near regions of large charge densities, electric field is more. Therefore, equipotential surfaces are closer at such places or crowded at such places. For sharp edges, there is a large surface charge density, or regions where large charge densities are present, their electric field intensity is large. So equipotential surfaces are closer at such places. Option D is incorrect because equipotential surfaces are not always equally spaced. The spacing between the equipotential surface depend on the electric field intensity, which varies in different regions. Okay, so spacing is dependent upon the electric field intensity. If it is strong in the region, then they are closely spaced. If it is weak in the region, then they are farther apart. So it is not equally spaced. Equipotential surfaces are not always equally spaced, which varies in the different regions. In area with a stronger electric field, the equipotential surfaces are closer together, while in areas with a weaker electric field, they are farther apart. Okay, so next question and next exemplar problem 2.9. The work done to move a charge along an equipotential surface from A to B. So from any 2 points on the equipotential surface A to B, we have to move a charge. So what is the work done? So option A is cannot be defined as this. Integral A to B E dot dl must be defined as minus A to B E dot dl, or C is 0, or D can have a non-zero value. So we know that on equipotential surface, potential difference between any 2 points is 0. Okay, so if potential difference between any 2 points on the equipotential is 0, so work done is also can be 0 na, or is also 0. So and it must be defined as this. So what is this E dot dl? This is not work done. Okay, and can have non-zero value. So I will give you some time to think about it. So C option is correct, which is 0. Solution. An answer. Work done in displacing a charge particle is given by W12 equal to Q V2 minus V1 and the line integral of the electric field from point A to point 1 to 2 gives potential difference V2 minus V1 equal to integral 1 to 2 E dot dl. So E dot dl integral 1 to 2 minus this will give the potential difference, not the work done. Okay, so for equipotential surface V2 minus V1 equal to 0, so work done is also 0. So work done is V2 minus V1. Okay, so V2 minus, if on the equipotential surface V2 minus V1 is 0, because at any point on the equipotential surface potential is same, so potential difference is 0. Since potential difference is 0, work done is 0. So this potential difference can be found using this thing. So the option A, that is work must be defined, work cannot be defined in this form or must be defined, the second option, so they are incorrect. This is only representation of the potential difference, not the work. So for work there is Q charge also. Okay, if Q is 1 coulomb, then work can be defined in this form. Okay. Next question, 2.10. In a region of constant potential. So in a region where there is a constant potential, option A, the electric field is uniform. Option B, the electric field is 0. Option C, there can be no charge inside the region. Or option D, the electric field shall necessarily change if a charge is placed outside the region. So I will give you some time. So option B and C is correct. The electric field intensity E and electric potential V are related as this: E equal to minus dV by dr. So if E equal to 0, this means V equal to constant by this thing, E equal to minus dV by dr. So if E equal to 0 means dV by dr equal to 0, which means V is equal to constant. So in a region of constant potential, electric field is 0. This implies that electric field intensity is equal to 0 in this region. Also, close integral E dot dA equal to Q enclosed by epsilon naught. This is Gauss theorem. According to Gauss law, if electric field in a region is 0, it means there is no charge enclosed by that surface. Okay, so if there is no charge enclosed by a surface, it means there is no electric field present inside that surface. So we know that electric field in that region where potential is constant is 0. So since this is 0, which means there is no charge inside. Okay, so option B and C is correct. Option A, which was electric field is uniform, is incorrect, because the uniform electric field implies a constant rate of change of potential. What is uniform electric field? It implies a constant rate of change of potential. But here potential is constant, not changing. So constant rate of change of potential implies the uniform electric field, not a constant potential. Constant potential implies 0 electric field. In a region of constant potential, electric field must be 0, not uniform. Why D option is incorrect? The electric field shall necessarily change if a charge is placed outside the region. This is incorrect, because the placement of charge outside the region of a constant potential does not affect the electric field inside that region. Okay, so if we place any charge outside the region, it will not affect the potential or electric field inside the conductor. The electric field inside a region of constant potential remains zero regardless of external charges. Okay, so if potential is constant inside the or in a region, electric field will be zero. It will not be affected by external charges. So our next question, 2.11. In the circuit shown in the figure, initially key K1 is closed and key K2 is open. Then K1 is opened and K2 is closed. Order is important. This order should be followed. Okay, firstly you have to do this, then you have to do this. Take Q1 dash and Q2 dash as charges on C1 and C2 and V1 and V2 as voltages respectively. Okay, so this is C1 capacitor, C2 capacitor, K2 key, K1 key, and this is the battery. Okay, so this is the arrangement shown in the diagram. These are the options. Charges on C1 gets redistributed such as V1 equal to V2. Charges on C1 get redistributed such as Q1 dash equal to Q2 dash. Charges on C1 gets redistributed such as C1V plus C2V equal to C1E. And charges on C1 get redistributed such as Q1 dash plus Q2 dash equal to Q. So I will give you some time to think about it. So correct answer is A and D. Solution. So what is the thinking process for this question? When key K1 is closed and key K2 is open, the capacitor C1 get charged. Okay, when this is open and this is closed, then C1 get charged by this battery. And when K is opened, when K1 is opened and K2 is closed, then there is a disconnection from this battery and C1 will get connected to C2 in a parallel combination. So when K1 is open and K2 is closed, the charge stored by the capacitor C1 get redistributed between C1 and C2. The charges stored by the capacitor C1 get redistributed between C and 2 till their potential becomes same. So they will reach at one common potential. Okay, so redistribution continues till their potential becomes same, such that V2 equal to V1. By law of conservation of charge, the charge stored in the capacitor C1 when key K1 is closed and key K2 is opened is equal to the sum of charges on capacitor C1 and C2 when K1 is open and K2 is closed. So when we open this K1 and close this K2, then the C1 will be connected to C2 in a parallel combination and potential. So the redistribution of charges will continue till the potential will be same on both the across both the capacitors, means common potential will be attained. Okay, and charges will remain conserved. Charges before the connection and after the connection with this C2 will remain conserved. That is Q1 dash plus Q2 dash will be equal to initial Q, that is on C1. So option B is incorrect because C1 does not get redistributed such as Q1 dash equal to Q2 dash. Instead, redistribution occur until the voltage across the both capacitors are equal, not the charges. The charges on the capacitor depend on their capacitance and final voltage. So charges will not be same on these capacitors because they are of different capacitance. Only charges will be same if they are of same capacitance. Okay, so which are generally not equal unless the capacitances are the same. So option C is also incorrect. The charge C1 on C1 does not get redistributed such that C1 V1 plus C2 V2 equal to C1E. This equation does not correctly represent the conservation of charge for the final state of the system. The correct relationship involves the conservation of charge and equality of voltages across the capacitor after redistribution. So this thing also doesn't hold. Okay. So thank you.